Yeah. So I welcome you to the fourth live interaction session of the course Introduction to Rings and Field. Myself, Harish. I am a PMRF fellow at ISR Mohali. So yeah, let's begin. So yes, it's live interaction. Session 24. Okay. So last time I want to discuss one question, but due to time constraints, I have to omit that. So maybe I will start with that question and then I will revise some definitions and terminologies and then we will see some other examples. Okay. So the question is, says let R be a ring. So again, by a ring I mean a commutative ring with unity with no non-zero nilpotent elements. I hope you all remember what is the potent element. It's just an element such that it's any power is not zero. So A is important if an is A is important if an is equal to 0 for some n. So what mean that R is a ring which has no non-zero important elements, only 0 is an important element. And other thing is if fx is a polynomial over such a ring, let's say fx is of this form. So ai's are in the ring R. So this polynomial is in the polynomial ring of R. So this is a polynomial and it's a zero divisor. So if you remember last time we saw what are the units in polynomial rings, and now this question is just an attempt to tell you how the zero divisors look like. But definitely I am making an assumption here that the ring has no non-zero nilpotent elements. So it's a zero divisor. Then one can show that and prove that there exists B in R which is non-zero such that B of A0 is equal to B of A1 is equal to B of A2 dot B of AM is equal to 0. So let me just change the notation because I will be using N for some other terminology. So what you see that if R is a ring with no non-zero nilpotent elements and fx is a zero divisor with polynomials over this ring, then there exists a B which makes each of the constant, each of the coefficient is 0. So if that coefficient is not equal to 0, then the coefficients are also zero divisors. Okay. So if you remember in the last class, we saw how the units look like in the polynomial ring. So if fx is a unit over a polynomial ring with commutative ring with unity, then a naught is a unit, and all this a1 to an is am are nilpotents. But now we are looking at how the zero divisors of such a ring look like. So if fx is a zero divisor over a ring with no non-zero nilpotent elements, yeah, one point is we can also omit this condition, no non-zero nilpotent element, this condition, but that will make the proof complicated. But you can definitely try and see that this is even true over any commutative ring with unity. Even without this condition, this statement holds true, and but the proof is a bit lengthy and complicated, so I'm imposing this condition. But just as a statement, you can realize that if you have a ring with units and commutative, a commutative ring, then there is explicit uh, uh, structure for a zero divisor. It has all the elements AIs to be zero divisors if they are non-zero, and if AI is any of the AI is non-zero, then there is a uniform B which makes them a zero divisor. So uh, as a statement, you can just realize that how good is that. So let us just try to prove that. Yeah. So are there any doubt on this statement? I think it's clear. Yes. Okay. So what we are given? We are first given that fx is a zero divisor over the ring Rx. So hence there must be a polynomial gx which after multiplying with fx gives you 0. So that's the starting point. So since fx belongs to Rx is a zero divisor, then there exists gx belongs to Rx, and definitely this gx has to be a non-zero polynomial. Gx belongs to Rx such that fx gx is equal to 0. So let's say this gs is summation bi x raised to I is from 0 to n. Okay, fx gx is equal to 0. Now what else? See, we are considering the degree of this polynomial to be n. So this definitely implies, or from here itself we can choose we have bn to be non-zero, because if bn is 0, then it's a polynomial of lower degree. So then and of course it's not a zero polynomial, so there has to be something non-zero. So bn is the highest, the coefficient of the highest power of x, so it is non-zero by just the definition of a polynomial. So non-zero polynomial. So now this is a non-zero element, and we are also assuming that the ring has no non-zero nilpotent elements. So this implies that bn raised to say k is not equal to 0 for all k belongs to the natural number, and this is because R has no. So this is the point where we are using the fact that R has no non-zero nilpotent elements, and we will use this uh, fact to proceed. Has no non-zero important. Okay. So here we have fx gx is equal to 0. So what is fx gx? Fx gx is summation of uh, j equal to 0 to n plus m. You have some coefficient ci and then sorry, cj and xj. Okay, that is 0. Okay, where because f has degree m and g has degree n, so this polynomial will has degree n plus m, and you can see that where your c naught is just a naught plus b naught. Oh, sorry, it's a naught b naught. C1 is a1 b naught plus uh, a naught b1, means the indices of A's index and B's index should add up to the index of C. Okay, and similarly you can see that C of n plus m will be just an bn. So comparing the coefficients of both sides. Okay, so comparing the coefficients of both the sides, you can see that this n plus mth coefficient here is an bn, but this in the RHS there is zero polynomial, so it doesn't have an cn plus m coefficient. So we at least get immediately that am bn is equal to 0. Okay, now not only that, we claim further that, so if you remember in the last class also, we use some kind of induction to prove what are the units in over the polynomial ring. So here also we are uh, intended to apply some kind of induction, because that will make our job easy. So how we can apply induction? By this step as the base step. So we claim that a m minus j a m minus j bn of uh, j plus 1 is 0 for all j between 0 and m. Okay, so you can immediately see that for j equal to 0, we are done. Okay, for j equal to 0, we just have, we have a m bn, and that is 0. Okay, so the base step is okay. Now so we can have the induction hypothesis and then try to solve the it for any j. So what is the induction hypothesis? So let us assume, so let me give it a number, maybe the first. Assume that one holds for all 0 less than equal to j less than equal to k minus 1. Okay, then for j equal to k we will show. Okay, so how to proceed with that? So we will go back again to the our initial step, that fx gx is equal to 0. And from here we were getting this coefficient cn plus c0, c1, cm plus 1 all are 0, because uh, the right hand side, in the right hand side we just have the 0 polynomial. So we will see the coefficient of, since fx gx is equal to 0, therefore we have c n plus m. I think I was writing m plus n or n plus m, that is okay. C n plus m minus k. This coefficient is also 0. Okay. And that will imply uh, what is C n plus m minus k? This is nothing but a uh, m minus k b naught plus a, sorry, not b naught, bn we should have, because the total index is n plus m minus k, bn plus a m minus m minus k minus 1 b of, it should be plus 1, yes, b of n minus 1. Remember, we can't increase go beyond m for the indexes of a, and beyond n for the indexes of b. That's why this kind of expression, you will start with m minus k and bn, then you will increase the indices of a and decrease the indices of n, and so on. What is the next term? It is just a m minus k plus 2 b n minus 2. And what is the last term? In the last term, you should have b n minus k, and b is n minus k, then a index should be okay. So this is equal to 0, right? Now what? Now one has to use the induction hypothesis cleverly. So we will multiply both sides by b raised to bn raised to k, multiply both sides by bn raised to k. Okay, then what will you get? This will imply that you have a m minus k b of n k plus 1 plus a of m minus k plus 1 b n minus 1 times bn of k plus dot 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 dot. You have am b n minus k bn raised to k, and that is equal to 0. So by induction hypothesis, you have to see this. So here you have a m minus j b and j plus 1. So if you put j equal to 0, then this is am, and you need one k to be 1. So here you have enough powers of bn. So let me just try it in a more uh, in a good manner, so that you can quickly see what is happening here. So this is a m minus k b n k plus 1, and you are subtracting k minus 1 from m. Okay, This is, so your j here is k minus 1, and then you can take this bn coefficients here. This is bn of uh, k minus 1 plus 1, that is k, and then you have b of n minus 1, and let me just write it after some gap. Okay. Then you have what's the next term? So next term is going to be a m minus k minus 2. Here you have b of n minus 2, and how many powers of b you need? You just need b uh, k minus 2 plus 1, that is uh, k minus 1 powers, and 1 bn is extra, so you can write it like that. And so you have more than what you require. Okay, for the uh, terms, you have enough of bn's. So here you have bn minus k, bn k minus 1, because total is b and k. Okay, this is equal to 0. Now you can apply the induction hypothesis part. So here j is k minus 1, because we have expression of this form: a m minus j b and j plus 1 equal to 0. So here j is uh, k minus 1, and okay, this part, and here j is k minus 2, and here j is 0. So we already assumed that the claim holds for all j less than equal to k minus 1. So we can write directly that by induction hypothesis, by induction hypothesis, we have what we have: a m minus k, bn of k plus 1. Here you have 0 uh, plus 0 dot 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 0. So everything vanishes, and that implies that you are just left with the a m minus k bn k plus 1 term, and that is what you were supposed to prove, because now j, if you put j it to be k, then it's just a m minus k bn k minus bn k plus 1. So this implies that claim holds for j equal to k as well. This implies an a m minus j b n j plus 1. This is 0 for all 0 less than j less than equal to 1. Okay, is it clear till now, or anyone has any doubt? We will look at the proof for a while. We will prove the statement now. For that, we needed just this claim, so we proved it using induction hypothesis. Yes. Okay. So if there is no doubt, then let me proceed. So what next? So we have this thing that a m minus j b n j plus 1. This is equal to 0 for all j between 0 and m. So what this means? This means that starting from 0, you have am bn equal to 0. Then after for j equal to 1, you have a m minus 1 b let me just write it stepwise. You have am b minus am bn is equal to 0 for j equal to 0, and then you have a m minus 1 b n what j bn square is 0 for j equal to 1. Okay, and for j equal to 2, what you have am minus 2 bn cube is equal to 0 dot 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 dot, right? And at the end you have a this holds till m. So when you put j equal to m, this is nothing but a naught b n m plus 1 is equal to 0 for j equal to m. But what we need to prove, we need to prove that so till here, see, this establishes this thing gives you that if uh, ai is not equal to 0, then ai is a zero divisor. Okay. Mm. Since bn of k is non-zero for all k belongs to n, that we so here for this part we use that ring has no this we have by this we can conclude that if either the coefficient of fx is 0 or it is uh, a zero divisor, so either 0 or zero divisor, and that is true for all coefficients. Okay, so but we were supposed to prove even a stronger condition, that there would be a uniform B which is making all of them a zero divisor. So can you just guess what is that B from here? What choice of B will make after
B0,
multiplying? Yeah,
B0.
no, B has to be non-zero for making it a zero divisor. If that would be the case, then we would have in the beginning of we would have said that uh, this is always true, right? If we take b equal to 0, but we want something non-zero.
No, not B0. It's B with index 0.
I couldn't get what.
B with index 0, I'm saying.
B with index
Not
0.
B0. Yeah.
What that means? B naught.
Like the constant part of that. Yes, yes.
But you will make am b naught equal to 0 and am minus 1 b naught equal to 0. Yes, Aniket. So you want if your B is choice of B is B naught, then you have to show that AM B naught is equal to 0, and till B naught you get 0. So this all these
Okay.
coefficients after multiplying with B naught is 0. But how will you show that?
Okay.
Did you get what's the catch here?
Hmm. That you can't do, I guess.
Yes. So from this set of equations, can you guess what is your B? What can be your B?
B equal to Bn.
B is equal to B.
N. B suffix N.
But see here you have am minus 1 bn square is 0. It need not that need not be true that am minus 1 bn is 0.
Oh, okay. So Bn raised by m plus 1.
B cube. Then you have problem in
Bn
b.
raised by m plus 1.
Then you will have problem in am minus 3 bn 4.
Uh, no, like m plus 1 is greater than 4.
Uh, can you just repeat what choice of b you are suggesting?
Yeah, B equals to Bn raised by m plus 1.
B is equal to bn raised to,
M plus 1.
yeah, that's correct. Okay, because see if am bn is 0, you just multiply this equation by bn raised to m, then still it remains 0. So just multiply both side with bn bm, then this will be what, this will be bn m plus 1 equal to 0. Similarly you multiply here with bn of m minus 1 and so on. Sorry, yes. So you can see that for all AIs we have good Aniket. So this choice of work. So from here, what we got that AI B and m plus 1 is equal to 0 for all uh, I belonging to 0. So for this choice of B will work. We will have it. So this implies for B equal to Bn m plus 1 we are,
Or
or
we can take any higher power also.
yes, good. Okay, so that's what I'm writing. So there are infinitely many choices. This implies we can take B to be Bn, say T, where T is greater than equal to m plus 1. Okay, yeah, and this is not equal to 0, that we have already seen here, because R has no nilpotent, non-zero nilpotent element. So what's the conclusion? Conclusion is that if something is a divisor of the polynomial ring, then uh, all its non-zero coefficients are also zero divisors. So you have explicit uh, uh, structure of zero divisors in the polynomial ring if R is a commutative ring with unity. Okay, and let me just write it, although I'm not going to prove it because the proof is a bit tricky. So remark is we can even drop the condition that R has no non-zero nilpotent elements. Okay, so what I mean that the above statement is true for all uh, commutative rings with unity. Okay, so I'm just writing CRE. And as in our course, we are considering just the commutative rings to unity. So this condition will always hold. Okay. And in fact, we will get, we are getting the uniform B. So, but why I am imposing this condition just to make the proof easier. Okay. So let me just remark that also. But the proof in this case is a bit tricky. Okay. It's not easy to see, but still doable. Okay. But for us, the statement matters more than okay. So we have explicit structure of units and the zero divisors of the polynomial rings. So I think that is good enough. And now we can move to the next topic. So let me just define some new terminologies, although they are already there in the lecture notes. But let me just, for the sake of revision, do that because they are going to be very crucial in the next classes. So if you have any doubt in those terminologies, then just let me know. So here is definition first. So do you know the concept of division in the ring? When we say that an element divides another element, if A is an element in a ring and B is another element, when we will say that A divides B,
So there exists another element C such that AC equals to B. In that case,
yes,
we will say that
yes,
A
yes.
divides B.
Okay, good. So let me just start
And
with that. Okay.
since it is commutative, so there is no problem doing that. AC or CA.
Yeah. Okay. So let R be a ring. So of course, by ring, I always mean a commutative ring with unity. R be a ring and A be a non-zero element in R because we want division by a non-zero element. AB belongs to R. Okay. We say that A divides B, or we will denote it or by this notation if there exists some C in R such that A is dividing B, B is equal to AC. Or as you said, as the ring is commutative, so it is same as writing C, B is equal to CA. Okay, so that's the notion of division in the ring. You can see your favorite ring to be uh, the ring of rationals for an quick example, but that is there for all elements you can define this kind of thing, but in arbitrary ring it's not necessary that you you are always able to define the notion of division. So be aware of that. Now let's observe few things quickly. So as remark, so this division definitely reflexive relation. A divides A, no issues. Okay, so A will always divide A because you know, as we are working with commutative rings within unity, so you have A to be just A times 1. Symmetry is not guaranteed. A divides B, uh, that does not imply B also uh, divides A. Okay. But this relation is, the division is also transitive. A divides B and B divides C. That will implies A divides C. So you all agree to that? That's not difficult to see. So I leave it to you guys. Fourth is A divides 0, because you can take any C to be 0 here. So A times 0 will become 0. So A divides 0 always. B, A divides C, that will implies A divides B plus minus C also. And sixth is A divides B implies A also divides BC for all C belongs to R. Okay. So these are the obvious, the first observations that you can immediately think of just after looking at the definition of uh, what is division inside a commutative ring. So now we can define what is called the greatest common divisor or the highest common factor for a commutative ring with the unity. Okay. So let me just write the definition of greatest common divisor. So let A and B are any two elements of the ring. Let A and B belongs to R. Then an element D of the ring, this set R minus 0 is called the greatest to be this is also called the greatest. See here I am using called a greatest, so that immediately tells you that I am defining it in such a way that it's not unique. So for two elements of the ring, there might be more than one greatest common divisors, but they have some relations among them, and that we will see in the next few minutes. But otherwise, I would have written here the greatest common divisor, but it's not unique. Okay, so let A and B are two elements of the ring, such that and D, some non-zero element of the ring is said to be a greatest common divisor. Greatest common divisor, and we will use the abbreviation GCD for it, or sometimes people also say highest common factor, or SCF. If what you guys think, what should be the property of a greatest common divisor?
So first
Huh?
D divides A and D divides B.
Yes, so first property is definitely, as it's a greatest common divisor, so first of all it has to be divisor. So D divides
Yes.
A and D divides B. So that makes it a divisor. Now to make it a greatest, it makes it a common divisor, okay? Because it's a
Yes.
divisor for both. So now what else? We need to make it the greatest of all divisors. Yes.
So if there exists a divisor C such that C divides A and C divides B,
Yes. So if C, so as we are talking about divisor, so we has to take it from the non-zero element. So if is a non-zero element, uh, such
such
that
that
C divides A and C divides B, then what?
C divides D.
Yeah, so C divides D. So all other divisors has to be smaller than D. Okay, and these two conditions will make it a greatest common divisor. Notation, what notation we going to use? We will just use the bracket A comma B notation for it. Let me just write this part. This another color. Okay, so I hope the definition is clear. It's not difficult, right? The first property says that it's a common divisor, and the second property says that it's the greatest of all common divisors. Okay. Okay, so notation. Uh, we will write D as bracket of A comma B. Okay, so this is the notation that we are going to give. Okay. Now, what else? So, as I said that mm, there might be more than one greatest common divisors, but they have some relation in common. So, for that, we need the ring to be a integral domain. So here is a lemma. Okay, it says let your R be a R be an integral domain 5, assuming that it also contains unity. Okay, because every integral domain in our setup is a commutative ring with unity first. Okay, so there if you have two GCDs, then they are just the multiple. So the second one is just a multiple of the first one by a unit of R. So what I mean, that R be an integral domain and AB belongs to R. Uh, uh, we have if D and D dash, they are some non-zero elements of R such that D is also a GCD of AB and D dash is also a GCD of AB, then there exists some unit in R uh, such that U is a unit in R and D dash is just D times U. So writing D dash as D times U, or you write D as D dash times U, they are just same because it's a unit. And once you have this, then you also have D dash U inverse is equal to D. So now you can take your unit to be U inverse, and then you can write it in terms of D. Uh, so what I mean that D is also D dash times V, where V is a unit. So this order of D and D dash doesn't matter, right? So yes, so if there are two greatest common divisors, then the first one is the multiple of the second by a unit and vice versa. Okay, so let's try to prove this statement. So we have d dash and d both to be just the units of to be the greatest common divisor. So they both satisfies the property of greatest common divisors, right? So see, since d and d dash are GCDs of A and B, therefore what you have, D divides A, and definitely D divides B, and D dash divides A, D dash divides B, right? But they are also the greatest of common divisors, right? So by the second property of GCD, okay, because see, using D is equal to the GCD of AB and D dash dividing A, D dash dividing B. So you can immediately use the second property, that since D is the GCD and D dash is dividing A and B, we have D dash must be dividing D, right? And what this implies? This implies D is equal to D dash times some alpha, right? Or some alpha in R, right? And this we have got using the GCD property of D. Let me just give it some equation first. Now using the other thing, that D dash is also a GCD and D is dividing both of them, right? So using that, what we have D must be dividing D dash, because D dash is a GCD. It's the high. It must be the greatest of all common divisor. So this will implies that D dash is equal to D times beta for some beta in R. Yes, you agree?
Yes.
Okay. So now by first, what you have? You have uh, D dash is D beta.
D equals to D times alpha beta.
Yes. Or I am just substituting D here. So D dash. Whose mic is this? You just mute him. Okay. Yeah. So I'm substituting the D from equation 1. So it's D dash. My D and alpha are looking similar. Let me just write it more clearly. So D dash alpha beta, right? Now at this point, we will use the assumption that R is an integral domain. Okay. So since R is an integral domain, this will implies that we have, first of all, we have D dash 1 minus alpha beta. It's a ring with unity. So we can separate 1 from D dash. This is equal to 0. And since your D dash is non-zero because it's a GCD and R is an integral domain. So if a product is zero such that one of them is non-zero, then in integral domain we must have the other to be zero. Okay, so therefore we must have 1 minus alpha beta to be zero, and that implies that alpha beta is equal to 1, and that implies alpha is a unit, and of course beta is also a unit. So d dash is d times some unit, and d is also d dash times some unit. Okay, so two common greatest common divisors are just like multiple of by a unit. So there is not much difference. You're just multiplying a unit to get another GCD. Okay, so this is one side, that if you have two GCDs, then they are related by this. Okay, and you can of course show that if D is a GCD, then D times 2 is also a GCD. Okay, there is nothing much to do in that. Okay, so I hope this is clear. If you have any doubt, then just ask me. Okay, otherwise we will see the other part. We haven't written if and only thing. Let me just write it in the bracket. Converse is also true. Converse is also true. Okay. So for converse, what we need to prove, if D is equal to the GCD of AB, then D times is also GCD of AB for all units U in R. Yes. Does anyone want to comment on that?
Yeah, so U is
Yes.
a unit, so they like universe is also a unit. Then
Okay,
D divides
let's
D
go step by step. So
U,
since we are given U is a
and
unit, therefore we have there exists V belongs to R such that
V.
UV is equal to 1. Okay.
Yes.
Okay. Now and what else we are given? D is the GCD of AB. Therefore D divides A and D divides B, which implies there exists say some alpha beta in R such that A is equal to alpha D and B is equal to beta D. Okay, and so we need to show that du is also what to say, it also a GCD. So first of all, these conditions should be satisfied, right? But so this will implies that A you can write as alpha times V, because we are in commutative ring setup, du, and B is also, we can write beta times V du, right? Since R is commutative ring with unity and UV is equal to 1. Okay. But what does this implies? This implies that du divides A and du divides B.
B.
So first, yeah. So first property is satisfied. Now what about the second property? So let's say if C belongs to R such that C divides A and C divides B. Okay. Then since D is the GCD, then using D, then using D to be the greatest common divisor, we have D divides C, right? And that implies that there exists some, say, gamma belongs to
C divides D.
R that
C divides D.
yes, yes. C divides D. Thank you. C divides D. So we have D to be C times gamma. Now we want that D C must divide your du. So this immediately mean that d of u is just c times gamma u, right? So we also got that du is divisible by c. C divides d. Okay. And of course, as we are in integral domain setup, since d is non-zero, u is non-zero, because u is a unit, therefore du has to be non-zero as your ring is an integral domain. So it's a non-zero element which satisfies the condition first and second. Thus, we have du is a unit. It implies d, oh sorry, not a unit, it's a GCD of. Okay, so it's an if and only if condition.
Uh, shouldn't we check also that du divides D? Like it's easy, but yeah,
Why we are supposed to check that?
like we have checked that C divides du. That means D divides du, but we also have to check that du divides D because then D is also GCD.
No, see, we are given d is a GCD already, and we need to show du is a GCD.
Okay.
Okay. Maybe I should have written this then to show du is GCD. Okay, so that we are supposed to show. So for
Okay.
that, first of all,
Okay.
du is non-zero, and then we just check two properties of it. Right, that's what the converse means.
Okay.
Right, Aniket?
Hmm.
Okay.
Yes.
So we have understood what is a GCD. Now let me define what is called associates. Because it's a good time to define it, you will immediately relate it with the above lemma. So let A and B belongs to R, then AB are called associates if there exists U belongs to R such that U is a unit in R and A is equal to B times U. Okay, so the elements of R which just differ by a unit is known as are known as the associates. So immediately you can see say that GCDs of for AB belongs to R. R is an integral domain. GCDs of AB are associates. Okay. And a small check is the relation of being associates is an equivalence relation. So when you have a commutative ring with unity, you can actually partition it uh, as the equivalence classes of associates. Okay, and that's not difficult to check. See, A is A dot 1, so the reflexive part is okay, right? Second is if say A is equal to B times U, that will then A U inverse is B, so that is also not a problem. And third is if A is B times U and uh, C is this right, B is C times V, then you have A to be C times V U, and V and U are units, so it's again going to be a unit. Okay, so it's transitive also. So it's an equivalence relation. Okay. Okay. So if that is clear, then let me just define what is prime element and irreducible element. Then we will again see some results. Till now, if you have any doubt, then you can ask me anytime. So definition of prime elements. So here we will take R to be a integral domain. Okay. If R is an integral domain, then any element, say P belongs to R, is said to be a prime element if what you guys suggest should be the definition of prime. So it has something to do with the prime numbers for sure. The intuition is that only.
For all AB in R, if P divides AB, then P divides A of P divides P.
Yes. But for that, one obvious thing is, first of all, P should not be a zero element, and we are not interested in taking P to be the units also, and P is not a unit in R. And the second condition is what you suggested. If A belongs to B, AB are in R such that P divides AB, then P must divide one of them. Okay. Okay. So you can have a look at this definition, and if you have any doubt, then just let me know. So the intuition is definitely the prime numbers. Okay. So now let us define what's called a irreducible element. So definition of a irreducible element. So again, we need R to be an integral domain. Let me use a different notation, maybe Q. Is said to be an irreducible element. If the first condition is like same, it has to be non-zero and it must not be a unit in R, and second one is a bit changed, not much, I will say. So if AB belongs to R such that you have AB to be equal to Q, then what you think it should be? What should be the conclusion? Then either A is a unit. So don't get confused between this A and this A is a unit, or B is a unit. Okay. So just look at these definitions. Can you find some connection between them? That whether a prime element is reducible or reducible element is prime? Definitely the first condition is same. What can you conclude by comparing the second condition of four of prime elements and irreducible elements? Yes.
Every prime element is irreducible.
Yes, every prime element is irreducible. Because if Q is a prime element, if you are able to write Q as AB, then A is a unit or P is a unit. That will imply that P divides A or P divides B. But here you have units, A to be units and B to be units. Might happen that A and B are not units, and still you have AB is equal to Q.
Then it means that Q divides like AB equals to Q, so Q divides AB, then Q divides A or Q divides B.
Yeah.
Q can't divide both A and B, because if that is the case, then Q square divides AB.
So let me just write some. So say if your Q is a prime element, right? Then definitely you have first condition to be satisfied, P not equal to 0 and P is not a unit in R. What about the second condition? So say if AB is equal to Q, right? For some A and some B, then surely you have Q dividing AB, right? Yes, Aniket and Muthu, you want to
Yes.
say the same thing? Yes.
Yes. Yes.
Okay. So since Q is a prime element, therefore this says either Q divides A or Q divides B, right? So if Q divides A, then what you have? There would be some alpha belongs to R such that A is Q times alpha. Okay, and that will use implication sign. That will implies that since your Q is just AB, A is AB times alpha, right? And that will imply A is 1 minus B alpha is equal to 0. And as you are in integral domain setup, R is an integral domain, you have 1 minus B alpha to be 0, and that will implies B alpha to be 1, hence B is a unit. Okay. And similarly, if you have you can show similarly that if Q divides B, then that will make you realize that A is a unit. A is unit. Okay. So what we concluded finally, that prime elements are also irreducible. Right? Okay. So with that, let me define two more definitions, and then we will again see some results. So till now, I think it's clear, right? If you have any doubt, then just quickly ask me. Otherwise, I will define the new notations or definitions. So yeah, if everything is clear, then let's move on to the next definition. So let me define the idea generated by some elements. Okay, so let R be a ring and A1, A2, dot, 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 AN are some elements of R. Then this ideal I R of A1. R of A1 is just the ideal generated by A1. Summing it with the ideal R of A2 and dot, 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 R of AN. This ideal is the smallest ideal is called the ideal generated by the set A1, A2, dot. And it's an immediate check that I is the smallest ideal containing A1, A2, AN, right? Okay. So if I is generated by a single element, then we say that the ideal is prime, principal ideal. If I is equal to RA for some A belongs to R, means it's generated by some a single element, then I is said to be sorry, to be a principal ideal of R. Okay. So if it is generated by a single element, then we say that it's a principal ideal. Okay. And any ideal which is generated by finitely many elements, that is said to be a finitely generated ideal. So that I'm not writing, but that's an obvious definition. Okay. Now we can define one of the most important uh, rings in the ring theory, which has a very vast uh, mm, theories inside it, and it has a very beautiful nature, and many things get uh, uh, more clear, and it's easy to understand a lot of concepts if you are working with that kind of ideals. So that is a principal ideal domain. So an integral domain is called a principal ideal domain if an, let's say an integral domain R is called a principal ideal domain if every ideal of R is a principal ideal. Okay. So as I said that many things becomes more interesting when you are working with principal ideal domains. So at least I should give some theorems or some results which make you believe that. So let's see one of them. If time permits, then we will have some more results, but let's start with this theorem. This says let R be a principal ideal domain. So I will use the notation PID for principal ideal domain, right? And so it's a principal ideal domain. So every ideal has to be generated by a singleton element. So let P, which is generated by say the element P, is a non-zero ideal of R be an ideal of R, then first property is P is a prime ideal of R if and only if this small p is a prime element of R. So prime ideals of PIDs are just the ideals generated by the prime elements. Sorry. Yeah, before stating that theorem, I should have given some examples and some non-examples. Yes, you should have asked for that. Yeah, can you quickly give some examples of PIDs? An ideal in which, a ring in which each ideal is a principal ideal.
Z.
Yes, Z is a principal
Is that
PID.
it?
Yes. What else? Uh, does any field is a PID?
Yes, every field that
Field is also a PID
yes,
that you can see, but I'm just stating that Q is a PID, R is
yes,
also a PID, and
C is a PID.
yes, definitely C is a PID.
Any field is a PID.
Yeah, it should be, no?
Because there are only two ideals, Z
No, their maximal ideals are just two.
and R in that.
That's not true. I think
Oh,
any field should also be PID. You can make it say some kind of work is needed, but I think that should be the case.
KX is a PID provided K is a field.
Yes, I am saying that every field is a PID.
Every field is a
I think so. No, because from integral domain to field, we go like that, like PID, Euclidean domain, and unique factorization domain, like that.
field has only two ideals. Ideal generated by 0 and ideal generated by 1.
Yes. So definitely, it's uh, PID, right?
Yes, every field is a PID.
So that's what I was saying, right? Okay.
What Muthu was saying, but that is wrong, I guess, because Z of X is not a PID.
What?
Z of X is not a
But Z is not a
PID,
field, na?
even if Z is a
ZX
PID.
is not a field.
Z is not a field, na?
Yeah, so okay, he was commenting
If K is a field, then
only about field.
KX is always a PID. That is true.
Yeah.
That maybe we will see in the next sessions. That is always
Yeah,
true.
that
If K is a field, then KX is a PID. Okay. So now what are non-examples? Definitely
yeah, Z of X.
Z of X, very good. And if you can also consider this example, the polynomials in with infinitely many variables. And here you can also consider the any field if you take, then also it's not going to be PID. Okay, because you can consider, say, the ideal generated by the odd indexed variables x1, x3, x5, x7, so on. That's not
n
going to
greater than or equal to 2
n greater
is,
than or equal to 2.
is not a PID.
Yeah, that also you can say, because C of x1, x2 is same as C of x1 over so you have C of x1, x2 is nothing but C of x1 and then x2, underline ring is Cx x1. Now this is a PID, not a field. So C of this need not be a PID, right? But that result I am not going to use because that we have not proved till now that K is a field and then Kx is going to be a PID. So, but without using that result, you can immediately see that this and these are some non-examples, because you can consider the ideas generated by, say, odd variables x1, x3, x5, or any sequence of natural number you take, and then corresponding to it, you take the variables, say x1, x3, then x6, x8. The idea is generated by an infinite sequence uh, of variable. That's not going to be a principal ideal, right? Okay, so uh, once you have examples and non-examples, then we can go on with the statement. So P is a prime ideal of R if and only P is a prime element of R. Now, what about the maximal ideals? P is a maximal ideal of R if and only if P is an irreducible element of R. Okay. Third one is P is a prime ideal of R if and only if P is a maximal ideal of R. So prime ideals and maximal ideals are same if you are in PID, and not just that. By the above three, you can also say that P is a prime element of R if and only if P is an irreducible element of R. So life get very easy when you are in PID. Okay. So prime ideals are maximal ideals. Irreducible and prime elements are same. So this statement you can just keep with you because it's a very important statement, and it's the first statement that we have seen which signifies the importance of working with PIDs. Okay, so let's start with the proof of the first one. Proofs are not difficult. So first statement says if P is a prime ideal of R, if and only if P is a prime the capital P is a prime ideal of R, if and only if it is generated by a prime element. So let's go with the forward direction first. So see, P is a prime ideal. What does this imply? That P is not equal to R and P is definitely not equal to 0. So P is not equal to R. That implies that this P is not generated by a unit, right? Otherwise, it would have been equal to R. So small p is not a unit, and p is not equal to 0. I should have write 0 ideal. P is not equal to 0 ideal. So that implies that p is not 0. So first property is satisfied. Now for the second property, let p divides some element ab. Okay, then we need to show that p divides a or p divides b. But p divides ab implies that there exists some alpha belongs to R such that AB is uh, alpha times P, right? But that is inside R of P, which is P. So this would have implies that AB belongs to the prime ideal P. Now, since P is a prime ideal, therefore you immediately got that either A belongs to P or B belongs to P, and that will implies either A is equal to uh, R times P or B is equal to say some S times P for some RS belongs to R, because P is just the ideal generated by P, right? So this implies that P divides A or P divides B, right? The other implication is also uh, easy. Just repeat the process, just trace back the process. So since P is a prime element, therefore P is non-zero and P is not a unit, and that will imply the ideal generated by P, that is P is not equal to 0 ideal, and it's also not equal to the entire R, right? So the first property of prime ideal is also being satisfied. Second property is let AB belongs to P. Then that will implies that AB is equal to RP for some R belongs to R, uh, and this will imply that P divides AB, and that will implies P divides A or P divides B, and then you can conclude that either A belongs to P or B belongs to P, right? So something is a prime ideal if and only if it is generated by a prime element, if you are in PIDs. Okay. Now the second part, I hope the first part is clear. If you have any doubt, then you can ask. Okay, if not, then let's proceed with the second part. So second part says that something is a maximal ideal if and only if it is generated by a irreducible element. So again, let's first prove the forward implication. So it's a maximal ideal, right? P is maximal. Now we have seen earlier that every maximal ideal is a prime ideal. So P is definitely prime. By first, we have P is a prime element. and we have already seen that each prime element is irreducible. This implies P is irreducible, right? So just by using the already proved statements, we can show the forward implication. Now for the backward implication, let us assume that there exists some ideal I between R and P. Then what happens? So at this point, we have to use that we are in if there is some ideal between P and R, then what we can say? First of all, since R is a PID, therefore this I must also be generated by some element, say what notation, maybe C. I is generated by, say, C. Then what? We have RP, which is equal to P contained inside I, which is equal to R of C. This implies that C unit is also, R also has unit. So RP definitely contains P, right? So P is always there inside RP. Yes. But that
Yes.
will imply, okay. So that will imply that this your P is inside R of C, right? And yeah, implies that P is equal to R times C for some R belongs to R. Now, since this small p is an irreducible element, element of R, therefore, what you have, either gamma is a unit or C is a unit. But if this gamma is a unit, then you can, if this is true, then what you have, this implies P is equal to gamma times C, and thus you have P gamma inverse is equal to C, or gamma inverse P is equal to C, which implies C is inside R of P.
Yeah.
Yes. So
Generated by.
RC, the entire RC should be inside R of P, because once C is there, P is an ideal, capital P is an ideal. So whatever, if you multiply it by an element of R, element of ring, then that is also going to be inside this ideal. So RC is contained inside RP, and that will imply what was our RC,
That
that
means
was
RP
just,
is RP.
yes. So this is in P, and P is already there inside I, so I is equal to P.
Yes.
What about this other part? Other part says that if you have C to be a unit, right, then what happens? Then C is a unit, then what is the ideal generated by C? This has to be R, right? And RC was just I. So you got either I is equal to P or I is equal to R. If I is any ideal between P and R, this implies P is a maximal ideal. Yes. So we have both sides implication. So something is a maximal ideal if and only if it's generated by a irreducible element. Okay. Now let's see the third property, which says P is a prime ideal if and only if it's a maximal ideal. So see this part, we have already seen that every maximal ideal is a prime ideal. Every maximal ideal is always a prime ideal. You can refer to previous sessions, and that's not difficult to see, in fact. Now the other part, so that was that is already done. Okay. Now let P be a prime ideal. Then one has to show that it's also a maximal ideal. So P is a prime ideal implies this. So P is generated by this, right? Small p. So it has to be a small p has to be a prime element by the first point, and every prime element is an irreducible element that we have seen a while ago. So it's going to be an irreducible element, and thus by the second part, P is maximal ideal. Okay, that follows by second. Okay, so there you have both sides implications. Now the fourth question, the fourth part, something is a prime element if and only if it's an irreducible element. So here also one part we have already seen that prime element are always irreducible, that we have already seen, right? Now the other thing, let's P be a irreducible element. Then what? This implies that the ideal generated by P, this is a maximal ideal, and all maximal ideals are of course prime ideals, and then by the first part, small p is a prime element. Yes. So are there any questions, any doubts? If there are, then you can ask. Otherwise, we will move to the last question of today's discussion. So you see that how beautiful the structure turns out to be when you are under prime principal ideal domains. Prime ideals are maximal ideals, irreducible elements and prime elements are same. You know precisely what are prime ideals. These are just the ideals generated by prime elements, and you also know the precisely what are the maximal ideals. Okay, so these four statements are very important. Now let us see how the GCD looks like when you are in principal ideal domain. Okay, and in principal ideal domain, you are always guaranteed to have a GCD. That's also a very big result. You that you don't expect in an arbitrary ring, but that is always true when you are in principal ideal domain. So the theorem is, let R be a principal ideal domain. Okay. Then for all xy in R, there exists D non-zero in R such that D is the GCD of xy, x comma y. So in other words, what I mean, GCD of any two elements. Of course, your xy must be from the non-zero elements. Okay, because if you take x and y both to be 0, then there is no point of defining the GCD. Okay, so what I mean, the GCD of any two non-zero elements always exists. So that's one more interesting property that PID gives you. And not only that, moreover, we also know that what this GCD, how this GCD can look like. So moreover, this GCD D, moreover, D has to be of this form. D is some lambda times x plus mu times y for some lambda and mu inside your ring. So not only the existence is guaranteed, but also the form of this is also guaranteed. Okay. So is the statement clear? So silence means that either it's not clear to everyone or it's clear to everyone. Okay, let's be optimistic and believe that it's clear to everyone. So let's try to see the proof. So let us define I to be the ideal generated by X plus the ideal generated by Y. So this is always an ideal, right? So B right, okay. Okay. Now since R is a PID, therefore this I has to be generated by a single element, that is C, right? Or more clearly, I should write that. Therefore, there exists some C in R such that I is R times C. Okay. Now, what? So we claim that this is actually the GCD. Claim. If you want to go with the same notation D, then you can choose it to be just there exists some D belongs to R such that I is equal to D. Claim is G is the GCD of X and Y. G is a GCD. Okay. So first of all, one has to see that D divides A and D divides B. So for that, so D divides X and D divides Y. For that, see X can be written as 1 dot x plus 0 dot y, and thus it's an element of Rx plus Ry, which is nothing but R of D, right? This implies X belongs to R of D, and which implies there exists some R inside R such that X is R times D, and that will imply D divides X, right? Parallelly, Y is equal to 0 times X plus 1 times Y, and that is inside Rx plus Ry is equal to Rd. So we have Y belongs to Rd, thus there exists some S in R such that Y is S times D, and thus D divides Y. So the first property of the GCD is being satisfied, that it divides both of them. So it's a common divisor. Now the second property of it, that it should be the greatest of all, that we need to check. So let C be a non-zero element of the ring such that C divides X and C divides Y. Then how can you say that C divides D? Yes. Are you guys there? Hello.
C divides X means C divides Rx for any R.
So C divides Rx for any R.
R in capital. Similarly, C divides Y.
So C divides X means X is equal to some say R times C, and thus if you take Sx, then definitely it can be written as SRC. Yes. So C divides each element of Rx and C divides each element of Ry. Yes.
So C divides Rx plus S.
Then C divides each element of Rx plus whatever element of Ry you take. Okay. And then as D is inside your Rx plus Ry, so C divides D. Yes. So let me just write it explicitly. So C divides X. This implies that C is uh, um, so there exists say R and S belongs to R such that X is equal to C times R, and Y is equal to C times S, right? So this implies that XY is definitely there inside R of C. So Rx plus Ry is contained inside R of C, and that implies that Rd is contained inside R of C, and since D is always there inside Rd, this implies that there exists some D in R such that D is equal to T times C, and that make us conclude that C divides D. So hence, by that we can say that D is the GCD of X and Y. And of course, since D belongs to Rd, which is Rx plus Ry, therefore definitely there exists some lambda, some mu inside R such that D is equal to lambda x plus mu y. So this establishes the claim. Yes, that's what we are supposed to show, that in over PIDs, any non-zero elements has a GCD for sure, and moreover that GCD is of this form, lambda x plus mu y. Yes, so I think we are uh, done with the time. So again, there were some nice questions that I supposed to discuss, but let's keep it for the next session. If you have any doubt in the in today's session, then you can ask. Otherwise, we will stop here.
I am attending 2 hours on Friday and 2 hours on Sunday.
Okay, nice.
But still I feel difficulty in solving assignment problems.
Oh, so what you want? Maybe I don't want to make this session at least assignment oriented, because I feel like there are some nice results and nice theorems that, like the one we started with, the explicit uh, structure of the zero divisors, that these kind, some things that is still left after the lectures and assignments that I wanted to discuss here. But if you want, then I can say the other instructor to make his interactions to be assignment oriented. I think he's already doing that, right? No, Muthu? He used to discuss assignment problems or something related to assignment problems, or no? Yeah.
I think this the other type of problems, not exactly.
Okay. So maybe I will ask him to discuss something more relevant to the assignments. Or if you want me to discuss, then I can also discuss. Let him discuss it, whatever he is discussing separately. What do you want?
I don't know what about the others are feeling.
So
Other participants, what they are telling.
So Vaishnavi, you want to say something on this?
Yeah, sir. Also, yeah, assignments are somewhat difficult to solve. So complicated.
Okay. So maybe from the next time, I will at least try to discuss what is being used to solve the assignments. Not exactly the problems, because problems I can't discuss because it's a graded assignment. But at least I will try to keep the sessions in such a way that the concepts that are going to be used to solve the assignment, that should be at least clear. Okay. And if you have a problem in, say, any particular kind of exercise in the assignment, then you can ask me, but I won't tell you the solution, but I can just let you know that what are the things that you need to use. Is that fine, or you have some other thing to say? Yes, both of you. Is that okay?
Yes, it is okay.
Okay. So after solutions, at least Muthu, you are able to follow,
But
because
for the most
sol
of the problems, they are giving only the answer.
okay, so they are not complete solutions. So you want me to discuss something from the previous assignment, or you want in the next lecture you want that I should come prepared for the next assignment?
I think we can discuss the previous assignments.
Okay, so till now I think 4 assignments have been done, right?
Yes, 4 completed.
4 completed. So which ones you want to discuss?
Before.
Yes, I couldn't hear. You were saying something? Which one?
So week 4, fifth
Week
sub,
4.
week 4, fifth.
Okay, so the last one. Okay, I will come prepared with that. And Muthu, you want something else to be discussed?
Okay, we will discuss in one class and we will see how that goes.
Okay, so uh, I will try to get prepared with the assignment 4, and I will have some spare questions also, so that if we are done with assignment 4 before time, then we will discuss those spare questions in the remaining time. Okay.
Thank you.
Okay, then. Thank you, Muthu. Thank you, Vaishnavi. So, uh, are there any other suggestions, or shall I stop here? Okay, so I hope that it's fine. So, uh, okay, then I will stop here. Okay, thank you. Thank you, both of you.